Welcome to this lesson on efficient plugging in for data sufficiency questions on the GMAT, and in particular, yes-no format data sufficiency problems. So let's begin just by talking about the question format for yes-no data sufficiencies compared to other data sufficiencies on the GMAT. So this is an alternative to the standard value data sufficiency format. So we're just going to assume, unless we identify a yes-no data sufficiency, that we're looking for one value as our answer. But for a yes-no data sufficiency, your answer is intended to be either yes or no rather than a value. So it's basically the difference between asking what is the value of x versus is x greater than y. But the answer choices are still going to be the same. So you're going to have those 5 constant options correlating to which conditions is or are sufficient to provide a definitive answer to whatever the post question is. And those options, of course, are A means that statement 1 alone is sufficient. B means that statement 2 alone is sufficient. C means that the statements alone are not sufficient, but together they are. D means that each statement alone is sufficient. And E means that neither alone nor together are the statements sufficient. Now, let's talk about the strategic implications of this slight variation from a value data sufficiency to a yes-no. So first, you're still going to evaluate yes-no data sufficiencies the same way as you would a standard value data sufficiency, either algebraically, arithmetically, or geometrically first. We want to do it mathematically. But we also have to recognize that always yes and always no are each sufficient outcomes. So the question of a yes-no data sufficiency, if I were to determine, using that example of is x greater than y, that no, x is always not greater than y, that would actually be sufficient. It's not just asking you, is the answer to this question yes? It's asking, can you determine if there is always a yes or no answer to the question that's posed? Now, plugging in does become a little bit more viable for yes-no data sufficiencies because there's such a wide berth of possibilities, either as yes or no. And we're going to talk here in this lesson about how to plug in strategically to minimize the number of scenarios that you need to model. And you're going to want to potentially reuse values in the plugging in process so that maybe you don't have to plug in repeatedly for each statement and possibly the statements together. You already have sufficient or insufficient scenarios that you can use for multiple steps of the process. Now, as part of this process, we're going to want to remember the acronym of FROZEN for data sufficiency plugging in. But first, we're going to want to begin our plugging in process by simply testing an easy value to determine one possible outcome, either yes or no, theoretically for a yes-no data sufficiency. Those easy values are going to be things like 2, 3, 5, 10, 100, or 1/2, and ultimately any values that are simple factors or simple multiples that are relevant to the problem. You just want to get one possible outcome of yes or no, because then you want to think about FROZEN, which is going to be an acronym that indicates different characteristics of numbers that might change the outcome because they have unique applications and impacts mathematically. So we'll then test strategically that FROZEN value in an effort to try to reach a different outcome. So what that means is, if I got a no for my first outcome with an easy value, I want to try now to get a yes. If I got a yes with the first value, my easy value, then I want to try a FROZEN value to get a no potentially. So the F in FROZEN is going to stand for fractions. You don't want to assume that every number, every plug-in value must be an integer. Remember that fractions are possibly viable. Then the R in FROZEN is probably the least mathematically related piece of FROZEN. It's just conceptually the idea of repeats. So like we said in the prior slide, the idea of minimizing the amount of testing that you have to do for the statements. So possibly the same value repeated, and definitely possibly numbers from the problem, because they're going to have unique impacts. So if we're told about 6 as being part of the problem, maybe we want to plug in 6 if there's a variable, because it may have unique impacts on the outcome. Then the next 2 letters are going to be individual numbers that start with O and Z that do strange things to math. First is going to be 1, because of course anything times 1 is just itself. Divided by 1, just itself. Raised to the first power, just itself. So there's a lot of unique characteristics of 1. And 1's neighbor of 0 is going to be the Z. Same reason, if you add 0 to anything, it stays itself. If you subtract 0 from anything, it stays itself. Can't divide by 0. That is something important to remember on some of the harder data sufficiencies. And then, of course, if you raise anything to the 0 power, it just becomes 1. Now, the E is going to be for extremes, and the way that you want to consider extremes is in terms of range. So theoretically, if we were presented with a data sufficiency involving 2-digit positive integers, we would want to test both 10 and 99, because whatever happens to 10 and 99 with our outcomes, all of the other pieces in between would have to be in between those two outcomes. So it's just a good way to test exactly what the ranges or the extreme edges of your possible outcomes are. And lastly is going to be N, which stands for negatives, because of course those have unique characteristics as well. And it's important to note that you're not really required to think about frozen in order. And in fact, many yes-no data sufficiencies or data sufficiencies generally will preclude some of the frozen pieces from being tested. For instance, if you're presented with a problem that says x is a positive integer, well, then I can't test the f, I can't test the z, I can't test the n. But if you don't have that restriction, you might want to consider what would happen with negatives. You might want to consider what would happen if your value was 0. You might want to consider what would happen if your value was a fraction. So this is a guideline, not a specific map to follow as far as frozen goes and testing weird values to get a different outcome. So let's apply this to a sample yes-no data sufficiency. So we have a setup here with just a little coordinate geometry drawing and a sample yes-no data sufficiency. And just as every other data sufficiency, we're going to begin by just articulating what we know. So we've got the point D, which is at the origin. So point D is at 0, 0. Then you can see that we've got area of triangle DEF, trying to figure out if that is greater than 6. And you can see I wrote down, theoretically here, a little y/n to indicate that I'm looking at a yes-no data sufficiency, not just trying to figure out what specifically the area of triangle DEF is. I'm just trying to determine if it's greater than 6. And of course, we box off that question so that we never lose sight of it. Then we've got to go to our need, and we determine that we are going to need to figure out the length of DF and the height. So the height of E is going to be our height for the triangle, and DF is going to be the base for the triangle, because you will create a right angle with the coordinate plane. So that means what we really need in order to determine the area of triangle DEF is going to be the x-coordinate of F and the y-coordinate of E. So then we take a look in condition 1. So we see that it tells us the y-coordinate of point E is 12. So pertaining to our need, we know this is telling us the height of triangle DEF is 12. And we can plug in to test whether we can get both a yes and a no outcome. So you can plug in values for the length of DF. And we'll just start with the easiest value that we came up with at the beginning of this, which is 2. So if DF is equal to 2, then the area of this triangle is going to be equal to 1/2 times 2 times 12, which is equal to 12. And the answer to our question, is the area of DEF greater than 6, is yes. So we've got one outcome. But then we want to think about frozen. And we'll just go straight to an easy value in frozen and say, what if DF is equal to 1? Well, in that case, the area of the triangle would be 1/2 times the base of 1 times 12, which is actually equal to 6. So in this case, is the area of DEF greater than 6? No, absolutely not. So because we have both a yes outcome and a no outcome, well, this isn't sufficient, and our options are going to remain B, C, E. So let's move on to considering condition 2. So we still have all the same information that we knew and needed and what the question was. So with condition 2, we're told that the x-coordinate of point F is less than 4. So this, as far as what we need, is telling us that the base of triangle DEF is less than 4. So we can once again plug in easy values for the base of the triangle. But we can strategically, from our frozen list, use the R of repeating 12 as a still viable possible plug-in value for the height, just to make things easy and know we can reuse it later if need be. So we'll keep the height as 12, And let's just plug in 2 as the x-coordinate of point F. So that would mean that the area would be 1/2 times 2 times 12, which is 12. And once again, the area of DEF is going to be greater than 6. So our answer to the question, is the area of triangle DEF greater than 6, is yes. And just like before, we will repeat the O in frozen of 1 and plug that in as the x-coordinate of point F. And that would make the area 1/2 times 1 as the base times 12 is the still viable repeated value for the height to produce an area of 6 for triangle DEF. And once again, is area DEF greater than 6? No. So at this point, we can eliminate B as a viable option because condition 2 by itself is not sufficient, and our options remain as C or E. So now we'll consider the statements together. At this point, we're certain that the height of the triangle is 12 and the base is less than 4. But we can repeat the values that already prove both a yes and no possible. So we already know that when 12 is the height and our x-coordinate is 2, that the area was 12, and the answer to the question, is the area of DEF greater than 6, is yes. And conversely, if the height of the triangle was 12 and the x-coordinate was 1, the area was equal to 6, and the answer to the question was no. So we have already proven that together, through our prior plugins, these two conditions are not sufficient, so we have to select choice E immediately. So once we find out that the two statements together are not sufficient, we automatically select choice E, knowing that the two statements together are not able to definitively say that always yes or always no, the area of triangle DEF is greater than 6. So let's take a look at the process that we just did in full. So step 1, as always, carefully read and evaluate the given conditions as mathematically as possible by asking 3 questions. First, what do I know? Note it with a K and the colon. Second, what am I looking for? Note it with the question, and if it's a yes-no format, always put Y/N just to indicate that clearly to yourself. And then just ask, of course, what do I need to find what I'm looking for, and you'll note that with our N. Now, step 2, if you're plugging in, you still want to carefully read and evaluate statement 1 as mathematically as possible, but you'll note the plugging in opportunity and plug in an easy value to determine one possible outcome to probably a yes-no question. Then you're going to plug in frozen values that we listed earlier to determine if the original outcome is constant, either always yes or always no. If always yes or always no for a yes-no data sufficiency, your choices A and D are going to remain valuable. If it is not always yes or always no, then your choices B, C, and E are going to remain viable. Then you want to efficiently plug in to evaluate statement 2. You'll plug in easy values and frozen values once again to determine possible outcomes to a yes-no question, or again, you could do this for a value. You'll use acceptable repeat values for statement 1 to expedite this process. And if your answer to a yes or no data sufficiency is always yes or always no, you'll choose B or D as appropriate. If it is not always yes or always no, you'll choose A if statement 1 was sufficient, but if statement 1 wasn't sufficient, you'll have to move on to considering the statements together, and only C or E will remain viable. And if necessary, because statements 1 and statement 2 were not sufficient on their own, you'll want to efficiently plug in to evaluate the statements together. You'll once again want to repeat values from statement 1 and statement 2's evaluations to maximize your efficiency if you're plugging in. And if together the statements are sufficient, you'll select C. But if together they are not sufficient, you will select E, whether that's for a value or a yes-no data sufficiency as you're plugging in. So let's go take a look at an example on the whiteboard of how you can use efficient plugging in for a yes-no data sufficiency. All right, so we have a sample yes-no data sufficiency here on the whiteboard. Pretty straightforward, of just asking, is the absolute value of x times x squared less than the absolute value of x times y? And so we'll indicate that with a little yes-no, that we're looking at a yes-no data sufficiency, and this is what we have. Now, Before we move on to our statements, we have to look and think, is there anything we can do to simplify this evaluation? So I know that if there are positive values on either sides of an inequality, I can actually remove them. And I know for certain that there are shared positive values on either side of my inequality because absolute value x have to both be positive. So we can actually divide the whole inequality on each side of it by absolute value of x, which simplifies what we need to determine, which is x squared less than y? So that's our question ultimately that we need to have answered in order to determine a definitive answer of always yes or always no to the question above of is the absolute value of x times x squared less than the absolute value of x times y. So we'll move on to condition 1. So we start with just y is less than x. So if y is less than x, and again, we don't know whether these are positive and negative, and that makes managing an inequality relatively difficult because you got to flip the sign, do a lot more technical, complex manipulation. So this might indicate a possible plugging in opportunity. So let's just plug in an easy value that will work for x and y. So if x is equal to 2 and y is equal to 1, well, then we know that we've got this original question of x squared being less than y. The answer is no. Because, of course, 2 squared is not less than 1, so simple enough. But we have to then think about our frozen values. So if we're considering frozen, well, I can think about a fraction. Because if x is equal to 1/2, and y is equal to 1/3. Well, now I know that 1/2 squared gives me 1/4. And even though y is less than x to start, 1/4 is actually less than y, and our answer this time to our original question is yes, x squared is less than y. So by itself, this condition is not going to be sufficient, and our options are B, C, or E. So then condition 2, well, this one's a little bit more easily evaluatable, right? Because it just says that x is greater than 2. So let's just say x is equal to 3, pick an easy number, and I have no idea what y is. So at this point, I probably can just go ahead and say this is not sufficient, knowing that there's no restrictions on y whatsoever. But if I want to prove it out, I could just say, well, if x is equal to x is equal to 3, well, then we know that it could be 9 is less than, say, 3 times 4, because if y is equal to 4, then the answer is yes, right? But if the answer is, say, 3 times 2, if y is 2, well, then the answer would be no to the question. So again, I can get to a yes and no pretty quickly, and I'm reusing values from the problem where I can for 2 as y. So by itself, condition 2 is not sufficient. So now we've got to consider the conditions together. And we want to eliminate plug-in scenarios that won't work when we combine the conditions. So I know right now that I can no longer do this option here that got me a yes when we plugged in a fraction for the value of x and asked the question of is x squared less than y. So now I know that x is greater than 2. So x is greater than 2 and y has to be less than x. So we know that y is less than x. So now we just have to go find values that satisfy that. Well, x can't be 2 anymore either, because we already said that it has to be greater. So x could be 3, it could be a weird thing like 2.1. So we know that we can get a yes out of this, because basically this no option is the only one that works together. Because I knew that y had to be less than the x is equal to 3, and I can't have y be greater than it anymore, so that one's out as well. So let's even just try something really strange like 2.1. So if I've got 2.1, so then we're looking at 2.1, and we've got, if that's equal to x, then x squared is going to be equal to, so 21 times 20 is going to be 420, so 420 plus 21 is going to be 441. And just put the point in, so 4.41, and 4.41 is still going to be greater than anything that y can be. So our answer is always no. And you can see that through this process, efficiently, we get to the conditions together being sufficient through some savvy plugging in without having to get into the more complex inequality algebraic manipulation. So go ahead and take this extra tactical approach of plugging in on data sufficiencies as you practice some GMAT problems on your own.